Assalamualaikum and good day everyone. So my name is Muhammad Rafuf Iman. I'm from the Mechanical Engineering program. So today me and my fellow groupmate will be presenting to you our topic which is application of Lean Six Sigma in Napco aluminum profile extrusion. So my fellow mate is Muhammad Akbar Haikal and also Muhammad Arif Farhan. And today we'll be presenting a case study that demonstrates how this methodology was used to significantly reduce the defect and improve efficiency in an actual manufacturing process. So I will begin by introducing the Lean Six Sigma, the tool involved, and the structure we'll be using throughout the presentation. So moving on to the next slide, which is about the table of contents for our presentation. So here is the overview of our presentation. We'll begin with the basic of Lean Six Sigma and how it helps improve quality and reduce waste. Then we'll be exploring the key phase of the DAMAT process. Next, we'll go over the core tool used in Lean and Six Sigma, followed by a deep dive into a tool applied in each DAMAT phase. After that, my team member will walk you through the actual case study from the Napco, starting with company background and how the methodology was applied in each phase. So for the next slide, which is about the introduction to the Lean Six Sigma. So the Lean Six Sigma or LSS is a powerful combination of two methodology. So which is the Lean is focusing on eliminating waste and making process flow more efficiently, while the Six Sigma, on the other hand, target defect reduction and process consistency. So LSS was first introduced in major companies like Motorola and Toyota and has since become a global standard for quality improvement. So its core goals is to deliver better, faster, and cheaper results by streamlining operation and reducing variation. So moving on to the next, which is the Lean waste elimination. So this is a major focus in Lean is on eliminating the 7 types of waste, summarized by the acronym TIMWOOD. So this include transportation, I is for inventory, M is for motion, weight, W is for waiting, O is for overproduction, and other O is for overprocessing, and the last one is D for defect. For example, in manufacturing, motion waste can occur when workers walk long distance unnecessarily, and overprocessing can be sometimes like double checking part that doesn't need it. For example, in the Napco manufacturing, which is moving aluminum profile between distance work area. So this falls under the category transportation. So by identifying and reducing this waste, we create a linear and more efficient system. So moving on to the next slide, which is about the DAMAT process overview. So the structure used in Six Sigma is called DAMAT, which stands for Define, Measure, Analyze, Improve, and Control. In the define phase, the team identify the problem and set the goals. And in the measuring phase is collecting the performance data. And during the analyze is to identify the root cause. In the improve is to focus on implementing solution, and in control is to ensure the improvement are maintained. So this structure ensures that every improvement is based on a real data and is sustainable over time. Moving on to the next slide, which is the tool and technique overview. So to make Lean Six Sigma work, we need the right tools. So Lean use tools like 5S, value stream, mapping, and Kanban in order to improve the flow and reduce waste. And using the Six Sigma bring in tools like control chart, Pareto chart, FMEA to manage quality and reduce variation. So each phase of DAMAC has tools that support it. For example, like CPOP and CTQ3 during define, and control chart and SOPs during control. So these tools help translate strategy into actionable improvement. So by applying this improvement, it helps to identify waste and variation, analyze data and root cause, implement improvement effectively, and sustain results through control mechanism. So moving on to the next slide. Now we'll be talking about more specific into the tools. So let's take a closer look at some of the specific tools. So during the define phase, we use CPOC diagram to map out the process at a high level and the CTQ3 to translate customer needs into measurable criteria. So in the analyze phase, we use the Pareto chart in order to help us focus on the most frequent problem, while the fishbone diagram to help identify a problem range of possible root cause. So each tool has its strengths and limitation, but together they give a complete picture of the problem. The next slide also is the continuous of the tool table. So in the latter phase, we rely on tools like the cost effect matrix in order to link process input to customer needs, and the FMEA to identify and reduce risk early. So when we reach the control phase, control chart help monitor whether the improvements are stable, and the SOPs checklist ensure everyone follow the same best practice. So these tools are especially important in order for ensuring that the improvement doesn't fade over time. So with that, I will now hand over to the next speaker who will walk you through the company we studied, which is the Napco, and how the Lean Six Sigma was applied in a real working setting. Thank you.
Hi everyone, my name is Farikal. I'll be presenting for the company's implementation of the Six Sigma. So the company that we chosen is Napco, known as National Aluminium and Profiles Company. It is located in Nablus, Palestine. Founded in 1991, Napco holds the distinctions of being the first aluminium profile manufacturer in the country. Over the years, it has grown significantly and is now part of the Arab Palestinian Investment Company, or APIC, with over 20 million in investments. The company has expanded beyond local markets to now export its products to neighboring countries. Napco operates a 28,000 square meter integrated plant equipped with advanced technologies producing aluminum profile systems for both architectural and industrial uses. Now, moving on to the Six Sigma implementation strategy, Napco adopted the DMIC methodology, which stands for Define, Measure, Analyze, Improve, and Control. The focus was on improving the process capability in the extrusion process and reducing defects, particularly in the geometry dimension D3 of product 4332, which was identified as the critical to quality characteristics. Their overall goal was to enhance product conformity, yield, and cost efficiency by reducing reparations in the process and tackling one of their most recurring defect types. So with that, let's dive into the define phase and see how they kick In the off. Define phase, Napco laid the groundwork by clearly stating their business case and project scope. They began with the project worksheet to define the title, the problem, objectives, and team members. Historical data analysis helped establish a baseline of their process performance before Lean Six Sigma was applied. Next, they used a CPOC diagram to map out the key elements of their extrusion process, from suppliers and inputs to the final customers. Using Pareto charts, the team identified that the System 7700, which is used for horizontal sliding windows, was responsible for nearly 48% of the defects. Within that system, product 4332 emerged as the top defective profile, mainly due to the geometry issues, specifically the D3 dimensions. The problem they defined was average defect rate of 12.38%, with the target being 10%. In 2017 alone, Profile 4332 caused 34 production failures. So the main objective of this phase was clear: to reduce geometry defects in Profile 4332, improve the conformity, the boost yield, and enhance customer satisfaction. During the measure phase, Napco used statistical tools to assess their current process performance. They ran a normality test which confirmed that the data followed a normal distribution. Then X bar and R charts showed the process was stable and under control, at least statistically. Next, they performed a process capability analysis. The target dimension D3 was 19.2 mm with a plus minus of 0.45 mm. But the results showed a CP of 0.67 and a CPK of 0.46, well below acceptable levels. The sigma level was found 2.88 with a defect rate of 8.96%, costing the company around 76,000 annually. They took 75 samples across 15 production trials over 35 days using high precision scanners and vernier clippers. Finding confirmed significant variation in D3, they reinforcing the urgency for process improvements. The measurement data gave a solid foundation to move into root cause analysis. In the analysis phase, Napco focused on identifying why the D3 dimensions was consistently out of spec. They began with a fishbone diagram categorizing possible causes in 4 areas, which is man, method, machine, and die tools. To narrow things down, a team of 7 experts used a decision matrix to evaluate 24 potential causes based on impact and frequency. From that, they found 62.5% of the issues were linked to human error and inconsistent method, such as lack of operator training and improper setup. Next, 25% stemmed from the die and tool issues, including worn out dies and incorrect assembly. And 12.5% were due to the machine factors like mechanical misalignment. The team then prioritized the most critical causes, those with 70% importance scores. This helped them focus their improvement efforts where it would make the biggest impact. With the root cause identified, Napco moved into the improve phase, where targeted actions were taken to resolve the key issues. Their strategy included: number 1, conducting focused training sessions to reduce operator mistakes and raise awareness. 2, routine die inspections and maintenance to prevent defects caused by tooling issues. And the last one, number 3, refining setup and alignment procedures to ensure consistency in the extrusion process. Each action was tied directly to a specific root cause using a cause solution matrix developed during the analysis. To avoid bias and encourage honest input, the team used the mini Delphi method, holding one-on-one meetings with plant leaders instead of group discussions. By the end of this phase, all corrective actions were fully implemented. The team then began collecting new data to compare performance before and after the improvement. The final step of the DMIC was the control phase, where Napco verified that the improvements were both effective and sustainable. They conducted another round of statistical analysis, and the results showed a clear improvement, with the process capability increased to 1.03, CPK improved to 0.69, sigma level rose to 3.57, defect rate dropped dramatically to just 1.57%, down from nearly 9%. This led to a 98.43% process yield and annual cost savings over 62,000. A major win for the company. To make sure that this gain would last, Napco put in place ongoing control measures, including quarterly monitoring on the D3 dimension and continuous statistical tracking through 2019. Thanks to this approach, the process remained stable over time and the improvement became part of the standard operation.
Good afternoon, everyone. Let's dive into the results of our Lean Six Sigma project at Napco. As shown in the summary table, this slide captures the key metrics before and after we applied the DMAIC methodology to address geometry defects in profile 433 to D3 dimension. Starting with the defect rate, we reduced it from 8.96% to just 1.57%, a massive 7.39 improvement. This means fewer faulty aluminum profiles, directly improving our product quality. Next, look at our process capability, our CP value, which measures how well the process fits within specification limits. It went from 0.67 to 1.03, an increase of 0.36. Similarly, the CPK, which accounts for process centering, improved from 0.46 to 0.69. These jumps show our process is now far more reliable and consistent. The sigma level, a measure of process quality, rose from 2.88 to 3.57, getting us closer to Six Sigma standards. Our yield increased from 91.04% to 98.43%, meaning nearly all profiles now meet customer specifications. Financially, this is a game changer. We turned an annual loss of MYR 330,000 due to rework into savings of MYR 272,000. Finally, the TPM, defects per million opportunities, dropped from 89,600 to 15,659, showing a significant reduction in errors. In short, this table proves that our lean Six Sigma approach delivered measurable improvements in quality, efficiency, and cost savings, setting a strong foundation for Napco's extrusion process. Let's move to the next slide to visualize these changes. Now let's bring these results to life with some visual trends. These slides include two charts that highlight the impact of our Lean Six Sigma project on Napco's extrusion process. The first chart, a bar chart, shows the defect rate for profile, dimension, before and after our intervention. In 2017, before we started, the defect rate was 8.96%. By October 2018, after applying DMAIC, it plummeted to 1.57%. That's an 82.5% reduction in defects, which is huge. This shows how our targeted improvements like better operator training and die maintenance directly reduce errors in the extrusion process. The second chart, a line chart, tracks the process capability index or CP over time. Pre-improvement, our CP was only 0.67, meaning the process struggled to meet specifications consistently. Post-improvement, it climbed to 1.03, a 53.7% improvement. This tells us how much the process is now better at producing profiles within the required D3 dimension of 19.2 mm plus minus 0.5 mm. What's exciting is that these improvements were a one-time win. Quarterly measurement through 2019 confirmed that these gains held steady, proving the sustainability of our changes. These charts show not just progress but a transformation in Napco's ability to deliver high-quality aluminum profiles. Let's now discuss what these results mean in a broader context. This slide dives into what the results mean for Napco and the broader application of Lean Six Sigma. First, let's talk about the effectiveness of DMAIC. By following its structured 5-phase approach, define, measure, analyze, improve, control, we pinpointed root causes like operator errors, inconsistent setups, and die wear. This led to an 82.5% reduction in D3 dimension defects for profile 4332 from 8.96% to 1.57%. That's a clear win for process quality. Financially, the impact is equally impressive. By reducing rework costs from 1,870 per ton to MYR 326 per ton, we achieved annual savings of MYR 272,836. This shows a strong return on investment for Lean Six Sigma, proving it's not just about quality but also about profitability. These tools we use like Pareto charts and fishbowl diagrams are scalable. We focus on profile 4332, but these methods can tackle defects in other profiles like System 7700, which accounts for 48% of the defects. This opens the door to further improvements across Napco's production line. We did face challenges, though initially, operators resisted new training protocols and die maintenance costs were a concern. However, with strong leadership, commitment, and phased approach, we overcame these hurdles. Looking ahead, there's potential to expand Lean Six Sigma to other lines and integrate real-time monitoring to catch defects early. This project isn't just one-off, it's a blueprint for ongoing improvement on Napco. Let's wrap up with our conclusions. Let's tie it all together now with our conclusions. This Lean Six Sigma project at Napco was a resounding success. By focusing on the D3 dimension of Profile 4332, we reduced defects by 82.5%, dropping the defect rate from 8.96% to 1.57%. This boosted our yield to an impressive 98.43%, meaning nearly every profile now meets customer specifications. The DMAIC methodology was key. Tools like fishbone diagrams helped us identify root causes, Pareto charts prioritize our efforts, and control charts ensured we sustain our gains. This data-driven approach eliminated guesswork and delivered measurable results. Financially, the project turned a 330,000 loss into a 272,000 in annual savings by cutting rework costs. This shows Lean Six Sigma isn't just about quality, it's about making the business more profitable. Napco's success reinforced Lean Six Sigma as a powerful framework for the aluminum extrusion industry. It improves quality, efficiency, and customer satisfaction, all critical for staying competitive. Finally, our quarterly monitoring through 2019 confirmed these improvements are sustainable. Thanks to control measures like standardized operation procedures, this project proves Napco can achieve world-class quality, and it sets the stage for even more improvements. Let's look at how we can build this success with our recommendations. To close, let's look at how Napco can build on this success. Here are our recommendations. For future improvements, first, we should expand Lean Six Sigma across other product lines like System 7700, which has a high defect rate. Applying DMAIC here could replicate our success with Profile 4332, improving overall process capability. Second, invest in technology. Automated die inspection system can detect wear early, reducing defects and ensuring precision in the D3 dimension. This could save time and cost in the long run. Third, enhance training. Regular Lean Six Sigma workshops for operators will minimize human errors and keep our process sharp. A well-trained team is key to sustaining quality. Fourth, introduce real-time monitoring with IoT-based sensors. These can track the D3 dimension during extrusion, allowing us to catch and fix issues instantly, preventing defective profiles. Fifth, collaborate with suppliers to ensure consistent aluminum billet quality. This reduces material-related defects, complementing our process improvements. Finally, foster a Kaizen mindset, a culture of continuous improvement, by encouraging all employees to suggest and implement small changes. Napco can stay ahead in quality and efficiency. These steps will help Napco maintain its competitive edge and continue delivering high-quality aluminum profiles. Thank you for your attention, and I'm happy to take any questions.